Here we have this two-mass system connected by a spring. It's stretched far from its equilibrium length. That means the spring is applying a force to try to restore whatever object it's connected to back to its equilibrium length. The objects are both released from rest and are pulled towards each other by the spring, which causes the objects to slide on a rough surface. Rough surface, to us, means that there is friction involved. That's a key that we need to deal with this with forces somehow. The coefficient of kinetic friction is mu. The students measure the momentum of the 40 kilogram object, shown as circles. If you're just looking at this and not seeing it on the paper, the circles are this top graph here, and then the 30 kilogram object is shown as the blocks. This graph, first thing we do when we look at a graph is look at our axis label and the units. So we have momentum, which is kilograms times meters per second, versus time, measured in seconds. They plot the momentum as a function of time for both objects. The graph is shown to the right, the diagram below. For the first part, on each block, draw and label the forces acting on the object while they slide. Okay, so let's go ahead and we'll do the easy one, the weight force, mg. Then that means we also have the normal force, Fn. We have the spring force pulling us this way, Fs. And then we have friction opposing sliding in the opposite direction. And the 30 kilogram object is going to look the same, but we will have a smaller weight vector, which means a smaller normal force vector. And we'll have the same length spring force because two objects, so object A is pulling on object B, so that means object B is pulling on object A in equal magnitude in opposite direction, Newton's third law. And then we have friction again opposing sliding to the right. There we go. Use the graph to calculate the net force acting on each object and the net external force acting on the two object system. All right, so looking at this graph, it is a momentum versus time graph. If I multiply these two quantities, I get that. My rise times my run. If I divide them, then I get my rise over my run, which is my slope. What does that mean for us? Well, what's the relationship between our change in momentum and change in time? Impulse momentum theorem, which says our change in momentum equals the force applied for some amount of time. So if I rearrange this equation, I get F equals delta P over delta T. So the slope of this graph equals my force acting on the object. So I can take my final momentum minus my initial momentum to get my rise. And then the run is full 2 seconds. So we have 40 minus 0 for the first object. 40 minus 0 is 40 divided by 2. So the force acting is happening in this direction to the right. So the net force, the stuff that makes it go minus the stuff holding it back, is 20 newtons to the right for object 1. So if I say M1, just kind of as reference, my net force is going to be 20 newtons, positive 20 newtons, because it's going to the right. If I look at my net force acting here, obviously the vertical forces are canceling each other out, so they're not helpful. My net force acting here, we can do the same thing. We can get the slope, which is negative 80 divided by 2. So negative 80 divided by 2 will give me a negative 40. And I'll write that again. M2 equals negative 40 newtons. Now what about the net external force acting on the two object system? If we have the two object system and we consider the entire system, so I'll draw my yellow line around the entire system. So both of these objects are now part of the system. Then we can look at the net force acting. So the net force is just going to be adding both of these forces together, which is going to be 20 plus a negative 40, which is the same thing as 20 minus 40. So the net force for the two object system is negative 20 newtons, or 20 newtons to the left. to the left. Now it'll be easy to do part C. Use the net external force acting on the two-object system to calculate the acceleration of the system's center of mass. Remember, when we're dealing with the center of mass, we're treating the whole thing as one object. We're just concentrating everything into one tiny little dot. So using this negative 20 newtons, remember the equation that we're going to be using is acceleration equals our net force divided by mass. Because we're dealing with the system as one object, that's your net force on the system, divided by your total mass will give you your acceleration for the center of mass. So in solving for the acceleration, we have negative 20 newtons divided by our combined mass of 70 kilograms. Negative 20 divided by 70 is going to give me an acceleration of negative 0.29 meters per second squared. I think. You are free to double check me. Use the net external force acting on the two-object system to calculate the coefficient of kinetic friction. Okay, so we know the net force is negative 20 newtons, or 20 newtons to the left. So if we're only looking at the kinetic friction, we can look at our frictional forces. So we'll have the friction on the 30 kilogram object, because that's going to the right, so that's the stuff that makes it go. So our force of friction on the 30 minus the stuff holding it back, which will be the force of friction to the left, which is the force of friction on the 40, equals the combined mass times the acceleration of the center of mass. Because we're treating this entire system as just one object, that's what's allowing us to do this. That makes our spring force an internal force. And does the internal force affect motion? No. So this is a problem-solving strategy to treat the whole body as one system. Now to solve for both of these, we know frictional force equals mu times mg minus mu times mg equals m1 plus m2. I'm just going to put that as 70 times 0.29, negative 0.29 meters per second squared. Mu, we don't know, it's mu, and I'm going to pull out that common mu. Mg for the 40 is going to be 400, minus mg for the 30 is going to be 300. So mu equals 100 in parentheses here. It's being multiplied by mu, so I'm going to divide it from the right side. So it's 70 times negative 0.29, which will give me 20.3 for my numerator. Divided, that's 70 times 0.29, divided by that 100 right here, divided by 100. So my mu will give me about 0.2. Less than 1, greater than 0. I like it. For the last part, let me clean this up. For this last part, we're using the value of mu and one of the net forces found in in A to determine the force that the spring is exerting on each object. All right, so to determine this force that the spring is acting on, if we do one object and it's the other, so we'll do the stuff that makes it go minus the stuff that holds it back. Right there, I chose the spring force pulling to the right to keep it positive. Frictional force is mu times mg. Plugging in the numbers, I used 20 newtons as my net force on mass 1. You get 100 newtons on each object.